our speaker. So Dr. Arvind K. Jain specializes in structural geology, tectonics, and Himalayan geology, and has worked in almost all parts of the Himalaya, from Ladakh and Karakoram to the easternmost parts of Arunachal Pradesh. He received his PhD from the University of Roorkee in 1970, where he worked with Dr. Rajin Misal in the Himalayas, and he joined the faculty at Roorkee in 1974 until his retirement in 2006, but he remains involved in the research community now. During his career, he was a member of various national committees of the government of India and select committees of universities and research institutions. He was involved in the establishment of 2 national facilities at the University of Roorkee and ITT Roorkee. And this is all in addition to handling various research and consultancy projects. He's written and edited 5 books, including an introduction to structural geology and the tectonics of the Indian subcontinent. He's published more than 120 papers and advised 15 PhD students throughout his career. He's fellow of the von Humboldt Foundation in Germany, Japan Society for Promotion of Science, and Indian National Academy of New Delhi in 2005. So with that, I'm going to open the floor for Dr. Arvind Jain to go ahead and deliver us his presentation. So Arvind, you're going to have to unmute yourself, and then you can, you've already got your screen shared, so you can put your video up. You're still muted. So we still can't hear you.
And thank you very much.
Okay, that's good.
Andre and Alex for arranging this lecture on where are the Himalayan rocks in the Himalaya.
Arvind,
okay.
One might be thinking,
screen.
Why this topic when we know it very well that the Himalaya is the youngest Cenozoic mountain belt on the earth and is still rising. Maybe by the end of this talk, I might be able to convince regarding the topic. The Precambrian sequences in the Himalaya were very well known since the beginning of the geological investigations because they were overlying fossiliferous Tethyan successions in the north, which were dated Cambro-Ordovician in the basal parts. However, extensive uranium-led zircon ages, both detrital and magmatic, and niobium isotope data available now for the regional correlation makes the things different, and hence I thought it better to take this topic. The objective of this presentation is to use the uranium-lead zircon ages and niobium isotopes in delineating the terranes in the Himalaya to find out the older orogenic events, the Paleogeographical reconstructions during the Paleoproterozoic and Neoproterozoic, and application to the Himalayan geodiversity. A few terms need better clarifications for this topic. The limits of the Himalayas are defined between Indus-Tsangpo Suture zone and Indo-Gangetic plains. The Himalayan rocks means any rock which is exposed in the Himalaya. It could be Cenozoic in the sub-Himalaya, Paleo-Mesozoic in the Tethyan Himalaya, Proterozoic in the Lesser Himalaya. Himalayan age, which is a very common term in the usage. However, it is confined to Miocene or maximum up to and maximum covering whole of Cenozoic. The uppermost part at times may be included, uppermost Cretaceous at times may be considered or may be included in the Himalayan age. There are evidences for the magmatism and metamorphism distributed throughout the geological period, especially since Paleoproterozoic. And hence the Himalayan magmatism and metamorphism includes only the Cenozoic, while the others are not included in this term. The age of the unfossiliferous sediments is deciphered by using the age of uranium-lead detrital zircons. This takes care of the youngest population of the zircons, a population of zircons, but not the individual grains. Individual grains does not define the depositional age, and the maximum depositional age of the sediments can be deciphered by this method. The Himalayan terrain covers distinct lithostratigraphic tectonic domains bounded by large-scale tectonic boundaries in the Himalaya. Why we use zircon for this kind of work? Zircon is one of the most common and resistant accessory minerals.
Arvind, can you pause for a second? I have a few people in the chat saying that they can't see the main slides. Is this the case for everybody? Can some people let me know?
No, I think
I can hear him.
We can hear, we can see also.
I can see the slide and hear him, but I can't see him. But the
Okay.
slides,
I think it may be people's view settings.
The video running. Actually, the video running.
Okay, so maybe it's something with other people's settings.
Yeah, it's okay here, Alex.
Okay, all right. Okay, it seems, so I think Greg and Dr. Pandy, maybe it's something rather with your settings this time.
They may need to go to the view section in the upper right-hand corner of their screen.
View options, right. Yes, so try checking your view options if you're struggling to see it. Okay, we're gonna keep this going. Sorry for the interruption. Please can go ahead and continue, Arvind.
Okay, and then my face is not needed during the presentation.
No.
Okay,
as much as we love it.
Yeah, maybe at the end. Yeah, should I continue?
Yes, go right ahead. Thank you.
Okay.
But it is much more common and widely distributed in all the three kinds of rocks. It survives extreme transport, magmatic and metamorphic events. Magmatic and metamorphic zircons can be easily identified, and it also records the growth at different geological times. And the timing of these growths can be easily determined by use of sophisticated instruments like TIMS, ICP-MS, SIMS, or shrimp. Let's try to see how the Himalayas look like. In the southernmost part, starting from the plains of what is known as the Indo-Gangetic plains, which of course are not included in the Himalaya. The southernmost part is the Cenozoic belt of Sub-Himalaya, which includes the Subathu, Dakshai, Kasoli, followed by the Shivalik group of rocks. It is bounded in the south by
Arvind,
the
can you move your
Himalayan
cursor up
Thrust
just a little bit?
and in
It's
the
at the
north
bottom of the
by
screen.
the Thrust.
Okay.
The next belt is the Lesser Himalaya, which is divisible into two sub-belts. The southern one is the outer Lesser Himalayan belt, and in the north we have the inner Lesser Himalayan belt. There is a very thick cover of the metamorphic sequence over these belts. The erosion of this metamorphic belt gives us the exposure beneath in various windows like the Kishtwar window, Kullu Rampur window, etc., where the inner Lesser Himalayan belt is exposed. The next unit is the Greater Himalayas, is exposed in the highest mountain and in the core of the Himalaya, which is divisible into three units. The southernmost is the Munsiari group of rocks, shown by the dark brown color. It is bounded by the Munsiari thrust at the base and the Vaikrita thrust at the top. The main central thrust, which is the most common and widely spread tectonic boundary rather, is the basal part is developed along the basal part of the Great Himalayan sequence, shown here by the pink color. The highest grade of metamorphism in the Himalaya is seen in this Greater Himalayan sequence. This belt of Greater Himalayan sequence is separated from the most important and well-known Tethyan Himalayan sequence, shown by the blue color, and is separated by the South Tibetan Detachment system, which is an extensional tectonic boundary, unlike the others, which are basically the contractional tectonic boundaries. Further to the north, we have a small exposure of the ultra-high pressure rocks in the submarine crystallines, and the northernmost tectonic boundary is the Indus-Tsangpo Suture zone, which separates the Himalayan rocks from the Trans-Himalayan and Karakoram, as well as the southern Tibet tectonic units. Our discussion is now focused more on the Great Himalayan sequence. As we have seen, that it is thrust southward over the Lesser Himalayan sedimentary belt, that's shown here by the yellow shade, and in turn this is thrust over the Cenozoic sub-Himalayan belt. if we look and integrate the magnetometric data with the geological data set, we can work out a tectonic model regarding the evolution of the Himalaya, where the Indian continental lithospheric subduction is now well established, where the Indian plate subducts. It possibly does not collide with the Asian plate, but it subducts beneath the Asian plate and can be traced up to Kunlun in Tibet. Most of the units become nearly subhorizontal and they are separated from the moho, as we can see here. A subhorizontal main Himalayan thrust separates the larger part of the Himalaya with a flat ramp geometry. We will now focus more on we'll focus more on the central part of the Himalaya, that is the Gulfal section, where a detailed investigations of zircons has been carried out recently and has been applied in our talk. And this approach has led us to different concepts of identifying the terranes. This section is along the Alaknanda Dhauliganga Valley, where the famous Badrinath is located. Here one can see the Vaikrita thrust and separating the Great Himalayan sequence from the Munsari group of rocks, which are thrust southward along the Munsari thrust over the inner Lesser Himalaya. The outer Lesser Himalaya is shown here by the light yellow color, and a tectonic boundary delineates this outer Lesser Himalayan sequence from the inner Lesser Himalayan sequence and is known as the North Harmora thrust. What is the approach towards terrain identification? One has to work out the geological characteristics, the uranium-lead zircon characters and ages, distinct niobium isotopic characteristics, so a selection of a well-known section, regional compilation of the uranium-lead ages, identification of distinct terrains with well-known tectonic boundaries. The selection of Alaknanda Dhauliganga Valley was done because detailed geological and structural data was available. Detailed textural metamorphic PT data was already carried out by Hodges and Silverberg, Spencer and others. And isotopic and geochronological constraints were also available, like in the publications by Ahmad, Cohn and Spencer. In detail, we have selected 20 samples shown by the rectangles, white rather squares, from the inner Lesser Himalayan sequence, the main central thrust zone, the Great Himalayan Sequence and the overlying Tethyan Himalayan Sequence, along with the whole rock SMND isotopic determinations on about 35 samples. Unit here is the inner lesser Himalaya. There are no Neoproterozoic zircons in this suite of rocks. O-line is the main central thrust zone, which locally is called as the Munsiari Grove. And there is a clippe of this MCT zone to the south. Again, two clusters are seen in these rocks, that is at 1892 and 1969, that is approximately of the same age as that of the sedimentary sequence of the inner lesser Himalaya. They also have the niobium values, which with an average of minus 25. That is, these are very, very low niobium values. The zircons are mostly euhedral with distinct oscillatory zoning and in general, there is a lack of the core here. The O-line Vaikrita sequence is interesting in the sense that we have the arrival of the Neoproterozoic detrital component here, which is basically in predominance, as you'll see in these blue distributions of the detrital zircon population. These ages range from 1050 to 850 MA, the peak being around 850 MA. Niobium values are much higher in comparison to inner lesser Himalaya, that is with an average of about minus 16. And possibly there is a younging trend in this about 10 kilometer thick metamorphic sequence. It is intruded by the Neoproterozoic and Paleozoic granitoids. The one which is seen here near the Vaikrita thrust, and another is seen near the South Tibetan detachment system. And this green one shows the Neoproterozoic granite. But interestingly, in this sequence and in this section, there are no Cambro-Ordovician detrital zircons. In contrast, the overlying succession, of course, with the tectonic boundary, that is the South Tibetan detachment system, we have the arrival of the Paleozoic zircons. The two sequences at the in the basal part, that is Martoli and Rolam formations, they gave a population which is with youngest zircon at 568 and 485 MA. The average niobium values is minus 16. Interestingly, there is a predominance of older zircons, with Neoproterozoic zircons being much more than the still older zircons here. If we summarize the data set from one section and then we will try to see the other sections in the Himalaya, we are struck with a distribution pattern, which is very characteristic. That is the inner lesser Himalaya showing a zircon population which is Paleoproterozoic. The MCT zone, which is basically here the granitoids, the malonitized granitoids in the MCT zone, show the similar population. The clippe of the MCT zone has also the similar population, whereas the still older, that is about, they are not Neo-Archean, but oldest Paleoproterozoic zircons can be seen continuing throughout the section, of course, with very little component. The sequence above the Vaikrita thrust has predominance of the Neoproterozoic zircons here, though the older zircons do continue. This is intruded by two granite bodies, that is the Cambro-Ordovician bodies, which are seen in the lower part as well as in the upper part. This is the overall distribution pattern of the Greater Himalayan sequence, in contrast to the pattern seen in the overlying Tethyan Himalayan sequence, where the Cambro-Ordovician component starts coming. If we compare it with the older Lesser Himalayan belt, the outer Lesser Himalayan belt, which is typically known as the Kroll belt, then we have a distribution as follows. This is some of the oldest work which are shown in this stratigraphic section. The sequence starts with the Mandhali formation, Chandpur and Nagthar formation of the Jonsar group. They are all siliciclastic rocks. And then we have an unconformity followed by the diamictites of the Bellini formation, which is typically taken as the glacial-marine. This sequence is then overlain by the Kroll group of rocks, followed by the Tal group, and then we have the Upper Cretaceous and lowermost Eocene sequence coming in, and then is the outermost and the southernmost clippe of the metamorphic belt. The oldest zircon work in this by Mairo in 2003, that is from the lowermost Tal formation here, shows the presence of Detachment zircons of 525 plus minus 8 Ma. The Bellini formation by Etny in 2011 yielded 770 and 692 Ma Detachment zircons. Of course, subsequently there had been numerous investigations, and now we have fairly good Detachment zircon population. The pattern is now better known. And what one finds here, if we find that the oldest zircon population is nearly Paleoproterozoic, followed by a good and substantial data set of late Paleoproterozoic raw Detachment zircon. And then we see a component of Neoproterozoic zircons starting from nearly 950 Ma in the Mandhali, and it becomes slightly younger once we trace the zircons in the younger sequences. In the Tal and Singtali formation, one finds the presence of the Cambro-Ordovician component here, mostly the Cambrian zircons, which can be traced up to the top. In the Singtali, which is taken as the Upper Cretaceous, one also finds a very small population here of Upper Cretaceous Detachment zircons. That's a new component which is not seen in any other formations of the outer Lesser Himalayan belt. The pattern becomes very distinct in comparison to the inner Lesser Himalaya, as we'll see in the next slide. In the inner Lesser Himalaya, the data set is available from the western part, that is from the Kulu Rampur window, going up to in Garhwal, Kumayu, and in Nepal, as well as it goes, we can see this population in Sikkim and then in Bhutan. And what one finds here, and this is what is being worked out by Gellers, which gives us an idea about the composite title zircon population from the inner Lesser Himalayan belt. The pattern is very distinct. That is, it is characterized by Paleo-Proterozoic zircons. That is around 1800. It's a nearly unimodal population in the overall context. That is a population which is nearly 1.6 to 1.8 GA. The peak is around 1.8 GA. And it is included, as we see, some of the well-known orthogneisses like Ulari here. It has some older component as well, but overall one see that the new zircons are nearly lacking, and it's mainly a single population sequence in the inner Lesser Himalaya. We can use this since zircon is not destroyed during the metamorphism and has overgrowth during magmatism, and it sustains long transport. One can use it for cross correlation across the different tectonic units. And this exercise in Kumayu and Garhwal shows that there is the lowermost inner Lesser Himalayan sequence in the Lesser Himalaya with characteristic 1.85 GA detail component, overlain by the MCT zone tectonically, which has similar 1.85 to 1.89 GA population across the various tectonic units like clippes like Askur, Badnath, Almola, Ramgarh. Then we have the Great Himalayan sequence with Neoproterozoic zircons, and Neoproterozoic zircons are also seen in Askur Bajnath, the Almola Nap, as well as the Ramgarh Nap. This is where the Nathogan formation is exposed. there is, and this is the pattern in the outer lesser Himalaya, which has a distinct Neoproterozoic to lower Cambrian Detachment zircons here. So the distinct that, and as one finds that there is a distinct pattern of the zircon population, and this is useful in carrying out and performing the cross tectonic correlation here. If we compare the zircon population across various units, that is outer and inner lesser Himalaya zircons, then one finds that the Paleoproterozoic zircons population characterizes the inner lesser Himalayan sequence, while the outer lesser Himalaya has Neoproterozoic to Paleozoic zircons. So this is very characteristic. One does not see this pattern in the inner lesser Himalayan groups. If we compare the Great Himalayan sequence, the Jutok group of rocks, the Tethyan Himalayan zircons, then we get a somewhat different pattern. We get now the Neoproterozoic zircons characterizing this belt along the Himalaya. That means right from the Satluj Valley, Garhwal here. This is the composite of the Great Himalayan sequence worked out by Gellers. And in Bhutan, then in coming further east, one finds a pattern which is very characteristic of the outer lesser Himalayan belt. That is the Neoproterozoic zircons. In the Jutok group of rocks in the Shimla Hills, one starts finding the presence of the Cambro-Ordovician component here. And this Cambro-Ordovician component, nearly at the boundary between Precambrian and Cambrian, can be seen in the Tethyan Himalayan sequence. One is tempted to correlate that the Jutok group could be a metamorphosed component of the Tethyan Himalayan sequence. After doing this exercise, we can then separate out the various terranes which are bounded, as I told you in the beginning, that is the different tectonic units bound the terranes. And hence, keeping in mind the Detachment zircon and the niobium isotope characteristics, one can separate four distinct terranes. The northernmost terrane is the Tethyan Himalayan sequence, which is being worked out as Paleo-Mesozoic Tethyan terrane here. The next is the Neoproterozoic Great Himalayan sequence terrane with characteristic Neoproterozoic component. The further south, we have the Proterozoic Lesser Himalayan terrane with three subcomponents, that is having a Proterozoic back arc basin, the outer Lesser Himalayan basin, and then a Proterozoic magmatic arc. And lastly, and all these ones are characterized, the inner lesser Himalayan sequence is characterized by 1.85 Ga zircons, the outer one characterized by Neoproterozoic Paleozoic zircons, and then we have the outermost terrain of Cenozoic subhimalaya, which is truly a Cenozoic terrain comprising of Subathu, Dakshai, Kasoli, and Shivalik group of rocks. So these four distinct terrains characterize the Himalaya. As we have seen that there are also patterns, there are also magmatic bodies within the Himalaya, which is basically pulsative in the sense that they are distributed in all the units, that is the Paleo-Proterozoic, Neoproterozoic, Cambro-Ordovician, Permo-Triassic volcanoes, and Cenozoic, what is known as the Himalayan. Because of this, that's the distribution of the various components of the Himalayan magma. Rather, is magmatism that is starting from 1.8 Ga onwards. I think it is wrongly written. It should not be there as Himalayan magmatism. The oldest one is the Paleo-Proterozoic here, Neoproterozoic, Cambro-Ordovician, which is a very widespread magmatic event in the Himalaya. Then there are Permian volcanics as well as the magmatic bodies. And then is the Cenozoic, which is truly Himalayan in age. There are also events of Cambro-Ordovician Metamorphism in the Himalaya. That is, the garnet SM&D ages worked out in Chor Mountains by Bhargav yield ages like 485, 473 Ma. In Alaknanda Valley, they give age of 534 Ma. The monazite uranium thorium ages from the northwestern Himalaya, that is 467 by Foster. In Tanawar formation of Pakistan, it is 482, 464. Central Nepal, it is 445. Namcha Magmatite orthogneis is 548. In Barun gneiss, it is 436. There are allanite inclusions in garnet, which is 445. And there are some older mica ages in Gondwana sandstone in Sikkim, which is 480. So all these ages reflect that there had been a Cambro-Ordovician metamorphism. Combining these magmatic events and the metamorphism, there have been efforts to identify if there had been some older orogenic events like in the Cambro-Ordovician. And this has been dated either as Bimpedian or Urgak orogeny. And what it amounts to? It amounts to rifting in late Eocambrian or Ediacardan age. It leads to the evolution of the Tethyan basin with a master fault. Because Tethyan basin, as we have seen, is a vast and enormously thick basin which accumulates a sedimentary sequence of about 10 kilometers, and most of it actually is shallow water except in the Cretaceous where it becomes deeper. So this leads to the evolution of the Tethyan basin. And then we have evidences of the early Paleozoic metamorphism, possibly in garnet grade. Then there is widespread early Paleozoic magmatism, the erosion deposition of Cambro-Ordovician sediments here. So various authors have called this event as Kurgyak orogeny in Zanskar by Srikantia 1977, Bhimkadian orogeny in Nepal by Kaud in 2007, Gellers in 2003, 2006, and evidences of Cambro-Ordovician granites cutting across regional folds, regional fabric, and thick skin thrusting. And this is also called as Kungan orogeny in Eastern Africa by Merritt. It leads to us for attempts to work out the paleogeographical reconstruction during the Paleoproterozoic and Neoproterozoic. There have been efforts to work out the transport of the sediments in the Great Himalayan sequence, because that becomes a very interesting part, that from where these sediments were derived. There had been efforts to postulate large-scale transports of sediments across various subcontinents by, say, Myro in 2010, with large-scale river systems flowing across the Archean terranes and bringing Archean as well as the Neoproterozoic terranes and bringing the sediments into a basin of North India. The another effort is by Lee, where the orogenic belts, Neoproterozoic orogenic belts, Neoproterozoic as well as the Mesoproterozoic orogenic belts have been worked out. And of interest is the presence of a belt of Aravalli Delhi Fold Belt, Central Indian Tectonic Zone, and Eastern Ghat Fold Belt here. This is of interest because we'll take this model into account. If you look at the paleogeographical reconstructions during the Paleoproterozoic, then one goes into a reconstruction of the presence of a Paleoproterozoic magmatic arc across North China, India, and North America. Now, if that is the case, then one deals with a presence of an arc here, the fore arc and back arc sequence. Now, let's see what this leads us. Now, this is basically a construction which gives us an idea about the presence of a Proterozoic magmatic arc in which tries to explain the presence of the magmatic bodies in the Munsiari arc with typical magmatic arc geochemical characteristics. Then in the back arc sequence, we have a vast sedimentary basin in which the inner lesser Himalayan sediments were deposited, which may be of the order of about 10 kilometers. Of course, the details are not very well worked out because of the deformation and their unfossiliferous characteristics. And this postulates the presence of the future outer lesser Himalaya, the Vidyan Basin, in this scenario. And further extreme south is the presence of the Indian crust, which had been responsible for shedding the 2.5 Ga tetrahedral zircons. Most of the 1.85 Ga tetrahedral zircons have come either by erosion of this magmatic arc or partly from the Indian crust. The presence of the Great Himalayan Sequence, which is a basin, Neoproterozoic basin, and the Tethyan Himalayan Sequence, which is a basin starting from 0.5 Ga, is shown here, but does not mean that it is a part of this setting. They are much younger in age. Detailed one. This is the latest Neoproterozoic body which has been discovered recently in 2020 by Sandeep Singh and his student. And this is the scene, a tectonic model, which gives us a distribution of the sediments in the Great Himalayan Basin. Spencer has also postulated, which appears to be a very strong case for Etonian magmatism and an arc in the north, which shed sediments to the Great Himalayan Basin. And these rifted bodies, that is the Neoproterozoic granites during the rifting of the GHS, is probably a remnant of this Etonian magmatic arc. Part of this is also being derived from the CITZ and the Aravalli-Delhi fold belt, and the Bundelkhand crust has provided the Archean component in this Great Himalayan sequence. This is the unit of the outer Lesser Himalaya, and then we have the Great Himalayan, the Almora Tepe here. So that's the scene we try to work out regarding the distribution of the sedimentary basins and the zircon population during the Neoproterozoic. So if we summarize, then we find that the Himalaya, as we understand, is mainly made up of, I insist that is mainly made up of the pre-Cenozoic assemblage of rocks. The truly Himalayan rocks, as we defined in the beginning, is confined only to the outermost sub-Himalaya. As a belt, of course, we have some lithogranite bodies which could be also called as Himalayan. But many of these lithogranite bodies, they have the core which is much older, and hence it becomes conjectural if we can really call them truly Himalayan. The Lesser Himalaya has got two terranes, outer Lesser Himalaya, which is essentially Neoproterozoic. The inner Lesser Himalayan belt, which is essentially a Paleoproterozoic back arc. The higher Himalayan has got two terranes, that is outer Paleoproterozoic magmatic arc, and GHS, Neoproterozoic terrane. And then we have the Tethyan sequence, Tethyan Himalaya, which has got Paleo-Mesozoic Tethyan terrane. So if you look into the distribution, we find that it is only the Cenozoic, outermost sub-Himalayan belt, which is truly Himalayan in age, while the rest of it made up of the pre-Himalayan sequence. The lesser Himalayan metamorphics has got Neoproterozoic zircons, extension of the lower grade GSS. The Jatobe metamorphics are basically composed of Cambro-Ordovician zircons, and hence it could be equivalent to Tethyan Himalayan sequence. Paleogeographically, we have the Paleoproterozoic assembly at 1.85 GA, that is the magmatic arc with inner lesser Himalaya as back arc, and sediment source from both Indian Craton and the arc. In Neoproterozoic, that is 1 to 0.8 GA, there's a back arc basin. The sediment source is from Aravalli, Delhi, Fold Belt, CITZ, Shillong, and the arc, and not from the outboard terranes. And zircon, as we see, is a very strong proxy for stratigraphic correlation for unfossiliferous sequence across different metamorphosed and tectonic belts, which are otherwise difficult to correlate. Paleogeographically, in orogenic belts, the fundamentals are the stratigraphic boundaries. That is, one has to identify the stratigraphic units, their characteristics, and correlation. This is primary. And tectonics and metamorphism, as we understand, is all secondary and superposed upon the primary relations. And how we can identify the primary relations, because many times in orogenic belt, because of the intense deformation, these are destroyed or rather obliterated, and hence one has to find means to that how we can identify the fundamental stratigraphic characters. And hence we find that the zircon is one of the most useful mineral for correlation, because it survives extreme events and also records the new events. This is one which is very useful, but then we had to also find other tools for the correlation across various tectonic. Thank you, Alex and Andre, for this series of seminars, which is definitely very useful.
Okay, great. Thank you so much for that. It's all really, really important information. This is the point where we transition to question and discussion. So we're going to give people an opportunity to ask a question, and you can ask in a couple different ways. If you do not have a microphone or would not like to ask your question for any reason, you can go ahead and type it in the chat, and I'll go ahead and ask it and read it off to ask it. Otherwise, if you would like to ask your question in person, you can either virtually raise your hand, or you can go ahead and type a star into the chat, and I'll direct you to unmute yourself and ask your question. usually it takes just a little bit of time for people to get their thoughts together if people want to ask questions.
Thank you very much, Andre.
Thanks a lot. Let me receive some clarifications or questions.
Sorry, Arvind, you're
I could-
a bit hard to
Thank
hear
you very
right now.
much, and Alex
Oh, I'm
for
sorry. I
arranging
think I have.
this lecture on where are
Rahul, just a minute. Yeah.
It was asked on the chat if the PowerPoint is available for download. We can discuss that with Arvind, but this whole presentation will be available on YouTube to watch again. Okay, it looks like there's a question from Beneath. So in a second here.
Thank you very much. The
Yeah, can I go ahead?
Yeah. Hello,
Yeah. Thanks a lot, sir. I mean, this was absolutely new to me, honestly, because I'm more into tectonics, more into earthquakes. But I just please excuse me if I'm wrong somewhere in my understanding. But I was trying to read, in past 2-3 years, I was trying to read about the formation of ADFB, its evolution, and then I stuck with the evolution of ADFB about 800 to 1000 MA, if I'm correct. So if that was the case, then so that means it's younger than the age which you put for the sediments which were transported from ADFB northward. I mean, I'm just confused. Probably I may be absolutely absurd in this.
No, you are not. Actually, ADFB has a collage of ages, which are from 1300 to 800 MA, or rather even younger, 750 MA. So,
okay,
and maybe part of this basin got filled in by the sediments which were eroded off from the Aravalli belt. Is it clear?
Yeah. Okay, got it. So it has got wider range of in terms of age. So
Yeah,
it is still possible.
And part of this sequence might have come from the central Indian tectonic zone, where again there is a very extensive ages available during which are of the Neoproterozoic in age. So, but not from the Eastern Ghat mobile belt, because as I understand that this CITZ must have been a barrier for the transportation of sediments from the Eastern Ghat mobile belt into the Great Himalayan Basin.
Thanks a lot. Thank you.
Thank you.
Okay. Any more questions?
I'm Anand here.
Dr. Pandi, go ahead. Yeah.
So that's great listening to my teacher, and but it created a lot of confusion to me. See, like when you find the source for the, let's say, higher Himalaya, inner lesser Himalaya, and so you get very similar age from east to west or west to east. But we do not have the same source in the peninsular region. If you, let's say, Aravalli, it is a very narrow belt. Then we go to Bundelkhand, Central Indian Suture zone, also restrict to the half of the Himalaya. Then in east, we go and find the rock which are not exactly same as in the central part of India, let's say Shillong material. So intention is if we have a peninsular component which are not homogeneous throughout, how come the sediment ages are continuous throughout the Himalayan late Proterozoic or Proterozoic basins which developed into Himalaya?
Okay. We are talking basically for the Great Himalayan Sequence. That was a Neoproterozoic.
I'm done.
Now, one has to understand few things. It has a component of very, very late Archean and earliest Paleoproterozoic detrital zircons. So you have to find a source for such zircons. That's number one. The second population, which is the most abundant one, is that of Neoproterozoic. Now, from where the Neoproterozoic zircons have come? So that is why there are various models which were suggested. Spencer, I think in 2018 or 2019, has postulated that there was a Neoproterozoic magmatic arc in the north which got destroyed during a orogenic event. But the evidence for that arc, which is he calls a Tethyan arc, are the presence of these Neoproterozoic zircons in the Great Himalayan Sequence. That's number one. And second thing is a very uniform character of the niobium values, which are -16 almost throughout the basin, right from extreme west to extreme east. So these are few things which have to be taken into account.
I have a small query, Professor Jain.
Yeah, please.
Yeah, only you mentioned in your talk that STDS is only the extensional system, rest of them are contractional system.
Yeah.
Yeah. So I mean, what is what is that extensional and what is that contractional?
Extensional one are the one where the movement has been towards north, and it is down deep movements, which is very characteristic along the South Tibetan detachment system. Wherever you go from Zanskar till extreme east in Bhutan, one finds this characteristic prevalent along this STD. Whereas the contractional ones are the one which there's a the other thrust systems like the main central thrust, main boundary thrust, and Himalayan frontal thrust, they are all taken as the contractional ones.
So if that is correct, so how would you justify that down the dip or extensional system in overall a contractional system? Because Himalayan mountain, or so that's the main point.
Kamal, I think we have to take another session for
okay.
answering this question.
Right.
That's a really interesting one.
Yes.
But then there has been a lot of work, and I think we have to discuss in person.
Okay, right, sir.
I have a question, Professor Jain. NC Pant here.
Okay, oh, great, Naresh. How are you?
Fine, absolutely. Now, I am really struck by one fact when there's a lot of geochronological data, and it represents Indian cratonic segment. And surprisingly, there is no record of any Archean ages here. Whereas there are evidence of, if I look at Wally's 2008 tectonics paper, from the Trans-Himalaya, there are Archean inherent ages which are reported. So what does it imply? Does it imply that there is no component of the Archean cratonic segment of Indian plate was involved in the part which under thrusted below, and why there is no Archean component, and what is the source of the Archean component in the Trans-Himalaya then? Thank you.
I think my reply would be very conservative in the sense that the fact is that there are no Archean rocks. Let me say it like that there are no Archean rocks exposed in the Himalaya. That is to the south of Indus-Tsangpo zone. At least I have not come across so far. what is seen are the detrital zircons with a very small population, which is very, very late Archean, not even older Archean times. So anybody calling that the Himalaya has Indian Craton rocks or Indian Craton extending into the Himalaya, I think is misnomer, at least to me, because I don't find any evidence of the Archean. I do not deny, I do not say that it is not present, but it is not exposed at this present level of erosion in the Himalaya. And for the Trans-Himalaya, I am not aware of that evidence which you are narrating. Maybe it is again an inherited zircon, which may be the case in many of the Himalayan sequences as well, but there are no rocks as such which are exposed in the Himalaya, which are truly Archean. Even
What I
late
meant was
Archean.
there is not even an inherent Archean signature in the from the Himalayan, as far as I understand from what you presented.
Yeah, right. I think you are right, and that's what I said, that my reply would be very conservative in the sense that maybe, say for example, you have say in Satluj Valley you have the Paleoproterozoic rocks exposed. Maybe somebody worked extensively on those rocks and might get some inherited Archean components. But the rocks are absent. Definitely they are absent, at least to present their knowledge.
Thank you. Thank you.
Thanks.
Okay, so Paul Hoffman typed up a question and comment here. It says, there are two Cenozoic collision zones in South Asia, the Indo-Eurasia and Arabia-Eurasia collision zones. They have much in common, north dipping subduction, but obvious differences in topography and structure. Why are they so different? Augusto Ganser worked in both.
Yes.
Perhaps a comparative study would be enlightening.
I do not know much about it, so I cannot, I think, answer that. The Suture zone, as worked out by Ganser in his 1983 paper, is basically a garland sort of a suture zone, starting from Pakistan going to Indus Valley, and then it takes along the Namcha Barwa, it takes a turn and go into the Mishmi Hills and go into the Myanmar. So that's basically a garland, but if there are any differences in that, I am not aware of that.
Okay. Do we have any more questions? I'll give everybody another minute or two or so. Or a few seconds to step up.
Professor Jain, can I ask one question, which I'm a novice in this field, but your lecture has really inspired. In fact, always your lecture inspires, particularly the younger generation. I've heard you several times. What is the role of tectonism, especially during the Miocene time, in driving the wind fields and ultimately the monsoonal, trajectories of monsoon strength, particularly during the Miocene time? I know you have spoken a lot about the Precambrian, Proterozoic, and like that, but any idea about the monsoon exhumation rates and tectonism? I don't see much on that from the Indian scientists.
No, we have worked on the various exhumation rates along certain sections of the Himalaya, but again, it's a very vast topic and one requires much more, exposure in that. But what is well known and a very common fact that the Miocene had been a time for a very extensive exhumation in the Himalaya, where most of the uplift has taken place, and naturally it has become a barrier for the monsoon, no doubt about that.
So this exhumation rate was more in the northwestern part of the Himalaya, or in the central part, or in the eastern part?
No,
of the
I think it's not that way. Whatever data we had, I think it is all tectonically controlled. Mostly it has a tectonic control, because the exhumation had been very, very fast in the window structures, right from the western part, say in Kishtwar, Kurlul, or Rampur. And in east, if we go, then there are few windows where we had the data set. In Arunachal, the monsoon precipitation is about 4 times than what you see in the northwestern part, but the exhumation rates are the same. So had it been controlled by erosion and monsoon, the exhumation would have been much faster in the eastern part, but it has not happened. There are certain areas in Kumayu, which are about 50 kilometers away from each other. The exhumation rates are different because they are controlled by tectonics, not by the monsoon precipitations. There's a paper by R.C. Patel on this aspect.
And I have one more question before I stop. You showed, this paleogeographic reconstruction, plate reconstruction during different time slices. I'm keen to know what was the position of Arabian plate since the Jurassic time, as it, or the, I'm mainly interested to know about the Oman margin. So, and of course the African Horn. So these two plate segments, have these moved since the Jurassic time to the north or west or east, or they have remained in the same place?
I don't have an answer to it. I think if I answer it, I would be fooling myself. So I would put it that way. And thank you, Anil, thank you, Anil, for supporting our efforts when you were director of Wadia Institute. It's only because of your encouragement we could get this kind of data set.
But sir, you were a driving force in getting that facility established at the Wadia Institute of Himalayan Geology. You helped a lot during the installation time, along with
that's so nice of you of acknowledging me, but from my side, it was you and your team which could make this collaborative program a success, and we could generate a lot of data sets. Thank you for that.
Okay, sir. Stay safe.
Okay.
Okay, Alex, Alex, I'm not asking a question. I'm just wanted to make a comment. The comment is simple, that the title of the talk is "Where are the Himalayan rocks in the Himalaya?" And the whole purpose of giving so many details about the Zircon geochronology and other things is to say that Himalaya, which is a Cenozoic element, is a phenomena. Himalaya came into being in the Cenozoic. So people think that there must be lots of Cenozoic rocks in the Himalaya, but the major bulk of the Himalaya is actually Proterozoic. So this is what has to be emphasized. This is what Dr. Jain has tried to emphasize, that the major bulk is nothing but the Proterozoic, not the Cenozoic element, and while the Himalaya itself is a product of a Cenozoic activity. That's all. Thank you.
Thank you, Diraj, for putting it nicely. And in fact, I could not do it in so many words, so many small words. But the fact is that the Himalaya has a very, very narrow belt in the south, which is truly Himalayan, that is Cenozoic, and the rest of it is Paleo-Proterozoic, Neoproterozoic, and Cambrian sequences. The Tethyan part is again Cambro from Paleo-Mesozoic. So in fact, in the Himalaya, there is hardly any rocks of the Himalayan age, and hence is the title that where are the Himalayan rocks in the Himalaya.
So I think, I mean, I was watching you talk a lot about 1.85 age zircons, and so and these being in back arc basin settings, and I think from what I've talked with Andre here, there haven't been a lot of iron formations found in India, but I mean, in a back arc basin setting there, if in the Paleo-Proterozoic, maybe we would expect to see some. Any indication of, you know, I know you're a structural geologist, not necessarily a sediment guy, but anoxic sediments, ferruginous sediments over there.
No, I don't think.
I can answer that.
Yeah, maybe DM Banerjee answers that.
Okay.
Yeah, there are ironstones, there are iron formations, and there are all Paleo-Proterozoic rocks associated with that. The extensive Paleo-Proterozoic phosphorite rocks are associated. The manganese of Paleo-Proterozoic manganese rocks are associated. So these beds are of his own character, his own they have different origin, and they have been interpreted differently by different people.
Okay, well, maybe I'll have to make my way out there sometime. Okay, well, I think if there aren't any other questions or for discussion, thank you very much for presenting today.
Can I just make one point?
Go ahead.
Yeah, Paul.
Yeah, I think that in defining, quote, truly Himalayan, we should be thinking in terms of those rocks that are associated with the Tethys Paleo-Ocean. And so therefore should include Mesozoic rocks as well as Cenozoic, perhaps beginning with Punjal traps.
Yeah, that's true.
And I would also say that I suspect that the reason for the paucity of Tethyan rocks preserved in the Himalayas is a function of the long history of post-collisional convergence and structural thickening and erosion of the northern India margin.
Oh.
Let
me put it this way, that as we understand the term Himalayan rocks, they are normally in our way of thinking, they are taken as Cenozoic, not the older ones. You know, say, okay, the Tethyan sequence were known since the very beginning, that they start from the Cambrian and go up to the late Cretaceous, and at places they are even Eocene, but they never thought to be Himalayan. What we understand by this term Himalayan, that's the basic thing. Is it, shall we start taking it from Permian onwards? Yes, then half of the Tethyan sequence would be Himalayan in age. Otherwise,
why retain concepts from the pre-plate tectonic era? This is not a good way to make progress.
Yeah, that's what I'm saying, that since the Himalaya is taken as the part of the collision between the two, but now even the collision is being debated. But let's not go into that debate. But that's basically a Cenozoic phenomena, and hence the question comes that what we include in the Himalaya. Shall we include everything in the Himalaya, or we separate the Himalayan part, that is the Cenozoic part, from the pre-Cenozoic? And if we separate it out, then the Himalaya as such, sensu stricto, has got very, very small component. That is the sub-Himalayan belt, and the rest of is basically the Paleo-Proterozoic and Cambrian sequences. Even the Cambrian sequences one gets in the outer lesser Himalaya also.
I don't think the Precambrian geology has anything to do with the Himalayas.
Oh, well, I think they have to do.
Didn't exist then.
If they come in force, I think they will unravel so many things in the Himalaya, for that matter.
We have unraveled a lot of things in the Precambrian in the Himalayas, and they are all in print. available in print in best journals.
Excuse me. I think that the Himalaya came into existence only after closure of Tethyan Himalaya. So Tethyan sequence are not Himalayan.
Yeah,
I think
right. That's what I'm saying. There is not Himalaya.
that's the
Don't-
answer to all.
Paul is not satisfied.
Okay, maybe that's a good note to end on today. So again, thank you very much for your presentation today.
Thanks a lot. Thanks a lot. Thank you very
Yeah,
much.
and we're looking forward to the discussion was really good. So thank you today, and looking forward to having you all continue to be here and present and interact with the seminar. So with that, we'll end for today. And if you want to join for next week, we're headed into the Ediacaran period for a paleontological view of the world there. So thank you, and see you all next time.
Okay, thank you. Thanks a lot. Thanks a lot, Alex, for all the trouble you have taken.